Hello friends, today I'm going to solve LeetCode problem number 63 unique paths 2. This problem is similar to problem number 62 unique paths. I have already created a video on that problem, so check it out on my YouTube channel. I'll also add the link on my description box below. And now let's get started with this problem. So in this problem we are given an m by n integer array grid, and we have said that there is a robot which is initially located at top left corner, okay, and the robot tries to move to bottom right corner, which is this grid square. Now the robot can only move either down or right at a point of time, okay. So down means from this point, which is the initial position of the robot wants to reach the end bottom right corner, okay. And the robot can only make a step towards the right or towards down. And we are also given that an obstacle and a space are marked as 1 or 0. So we have obstacles on our grid which is marked by value 1 as shown here. This is an obstacle and this is marked by value 1 in our given example, and spaces are marked as 0. So the robot can only take the path which do not have an obstacle, okay. So since this is an obstacle, the robot cannot step over this square. So the robot can either move this way, and from this if it can move right and it can move down, right, but it cannot go this path. Why? Because we have an obstacle over here. So this is basically what the robot needs to take into consideration to make its decision to move towards right or down, right. Now let's look at the constraints. We have the length of obstacle grid and the breadth, which is the number of columns, and the values are from 1 to 100, and each grid square has either 0 or 1. Okay, so now let's take this example, copy and paste it over here, and let's see how we could solve this problem. So what are we given is we have the robot, we have obstacle, and we have the end point where we want the robot to reach. Now starting from this point, the robot can move right or down, right. And what is our final product? Our final product is that the number of possible unique ways, right, ways to reach the bottom, and it should be unique. Okay, so in this problem I'm just going to explain like how are we going to tackle the obstacle, because the unique ways to reach the bottom I have already explained in my video on problem number 62 unique paths. So if you have not checked it already, please check it out. And now let's get started with this one. So now we need to find the unique ways. What are we doing is we are actually going to use dynamic programming here. And why dynamic programming? So let's see. So from any point robot can move either right or down, right. Now if the robot starts from this point, is at this point, then what's the possible number of ways to reach our target? So it's only one way, right. So that is what we are going to do here. We are going to find the number of ways for each of the square. So from this square, only one way to reach this. It cannot go towards the right. From this square, it can only move towards the right, so that's only one way. Now what about from this square? It can only go towards right, right. There is no square towards down. It goes out of bounds. So it has only one way, that is this way, right, from here. And similarly from here, it cannot go this way because there is an obstacle, so it can only go down, and that would be equals to one way, right. From this point it only has one way, so that's also one. From this point also it's only one way, so this is also a one. It cannot go down because there's an obstacle. And finally, from our starting point, which is this one, it can go towards the right and it can go towards down, right? So from this point it can reach the destination in one way, and from this point it can reach the destination in one way. So this, from this point, would be two ways, right? Addition of these two values, and this is our final answer. So basically, this is a recursive approach, a DFS approach. What we'll do is we start from the top and then we keep on moving towards the down and towards the left, and we perform a DFS until we reach our destination, and we keep on updating each of these values until we reach our final destination, and then we change the direction. That is, while we were going down in the first place, now we start going right, and so on, right? So this is a recursive DFS approach, and we can also solve it using tabulation approach. So for that, what we need is, as we have said, that we can go down, right? Down. So from a position, from an ith row, we can go to I plus 1 row, and from the jth column we can go to j plus 1 column, right? That is towards the right. So from each square we can go I plus 1 and j plus 1. So if we are at this position, okay, so we can go down, we traverse towards the left also, right? I mean towards the right. So j plus 1, since we are trying to look for this position and this square here, what we are going to do is we are going to create a matrix. Let's call it TP, dynamic programming, because of course we are going to use it in that way. And this, the length, this would be of n plus 1 rows and n plus 1 columns, okay? Because we are going to add an additional row over here, and all of these values will be equals to 0, and an additional column over here, and all of these values will be equals to 0 too, except we will change the value of one of these. Okay, let me just clear these things. This is our DP array, and in our DP array we will fill all the values with 0. So we are not modifying the actual obstacle grid array. This is our DP array, so we are filling all of these with 0. And now what we do is we change one of the values in our last row and m minus 1 column. So this is this is n minus 1 column, right? N minus 1 column and mth row to equals to 1. So from this point we try to look towards the right and towards down. So we add these two values. From this point, basically we add these two values and we find the number of ways for this one, and in that way we get the value equals to 1. Similarly, we will do it for all of the rest of the squares as well. So the next one we would be checking is this row, this is square, and for this also we go towards the right, look towards down as well, and then we add both the values. So now that value is equals to 1 over here. Similarly, for this one also we look towards the right and towards down, and we'll get the value equals to 1. And that is what we do for our next row. So we look up right and we look down, and we then update the value to be equals to the sum of those the value this downwards and value towards the right. Okay, and same here. So now here, okay, we have an obstacle here, so we will not be able to go through this path, right? So that is why we do not update the value over this path. Now what about this one? We go towards the right, we see that it has a value 0 and the value towards the down, and we update it. So now this value is equals to 1 here, right? And same here, so we update this one. Okay, this one will be 1 plus 0, so that is equals to 1. This one also be 1 because the value towards right is 1 and a value at down is 0, and this one will be 1 which is towards the right and 1 which is towards down, so that will be equals to 2. So finally we find our answer at this index, which is at 0th row and 0th column. So that is how we can solve this problem using tabulation and using recursive DFS approach. And why are we using DP here? So let's suppose if we have if there was no obstacle over here, then this could be reached from this square and from this square too, right? So in that case we are traversing this square twice. So if we save the value of this square in our first calculation, then in the second time we reach this square, we do not have to calculate it. We'll rather use the value stored in our cache memory to get the values, right? So we are avoiding repetitive calculation. So that is why we are using DP there. Okay, so now I hope you understand the solution, the concept. Let's try to dive into the solution. So I'm first of all going to use tabulation method, and I'll also be using DFS approach for that. So let's get started. So let us first define M equals obstacle grid dot length. Okay, and N equals to the number of columns, right, which is obstacle grid at index 0 dot length, length. All right, and okay, let's check one more thing. Now what if we have our obstacle at the point, at this point itself. If there is an obstacle at our last square, that would mean that no matter which path the robot takes, it will end up on an obstacle, right? And it can never step on an obstacle, so it will never reach this square. So in that case we are going to return a 0 because there is no way at all. So if obstacle, okay, I'm just going to copy and paste this thing, obstacle grid at index m-1 and n-1 is equals to 1, then we are going to return 0. Okay, now let us create our DP equals to new array of length m+1, and we are going to fill, okay, we don't need to fill it, and let, okay, so I'm just going to use a for loop here. I is less than m plus 1, I plus plus, and then we are going to DP at index I will also be an array of length n plus 1. Okay, now that we have created our DP, which is of 2 dimensions, let's start our for loop. So our for loop is going to start from which position? Our for loop is going to start from this position, right? Because we are starting from here, we are looking from the end, and we look towards these two directions, right? And also we need to make one of these as one, this column as 1, so that would be at column n-1 and row m. Okay, so let us do that also. So let dp at index m and column m-1 equals to 1. Okay, and let us fill all of these values with 0. We do not need a let over here. Now let I equals to, starting at the end, n-1, and I is less than n, okay, greater than equals to 0, I minus minus, and for let's do it m, let j equals to n minus 1, j is greater than equals to 0, j minus minus. Now we need to check if that column, that index is an obstacle. If that's an obstacle, we just mark it as 0, right? It will still be 0 because there is no path from that point. So if obstacle grid at index I j is true, then continue CUNTI anyway. Okay, we are going to continue, else what we need to do is dp at I j will be equals to, and now we look towards the right, which is index I j plus 1 plus dp towards down, which is the row below it j, and that's it. And then finally we return our dp index 0 0. Let's try to run our code and check if all the things work fine. Okay, so we are getting an error here. Can read it properly. Let's run our code. Great, now let's try to submit this thing and let's check if it is submitted. Awesome. So this is one way we could solve it using a for loop. And if you look at the time complexity, so we are iterating twice, right, over all the rows and all the columns. Basically we are iterating over all the rows and all the columns. So the time complexity is O of n squared. Also we are creating a dp of length m and n, right? So the space complexity is also of n times n. So that is about this solution, this approach. Now let's try to approach this using a recursive method. So for recursive method, okay, what we're just going to do is we are going to create a DFS function, and here we are going to pass our indices, of course, yeah, because we need indices to know which square are we on our grid. So now here also we are going to check these things. So let's just copy and paste it over here, and here we do not continue, we return. Okay, let me just cut and paste it over here. Okay, we return, and now next what are we going to check is if our dp has already been calculated, then we are not going to calculate it over again, right? So if dp at index ij is already calculated, so that will not be equals to 0. So in that case we return our dp at index ij. Else now what we need to is we need to calculate the dp, right? So we can move towards the right and towards down. So initially the number of ways is equals to 0, and then we try to go towards down. So to go towards down, I plus 1 should be less than m, right? So if that is the case, then we go towards down equals dfs and then I plus 1 j. Similarly, if we are trying to go towards the right, then j plus 1 should be less than n, else it will go out of bound, and right will be equals to dfs I j plus 1. Okay, now that we have the number of ways that we can go towards the right and towards down, so finally what we do is we add both of them, and this will be the number of ways we can move from this given index, right, down plus right, and we are going to return the value. Okay, so this is all about this one, and we are going to return our DFS at index 0 0. Okay, now let's try to commit this, and run this one. Oh, so we got a 0 over here. Okay, so one thing what we need to do is we only need a dp of length m and length n for this case, and here m minus 1 and n minus 1 should be equals to 1, because like if this is the point we need to reach. We mark this as 1, and now if we are at this point, we are going right and we are going down, so we cannot go right, so that's 0. We go down and here the value is 1, so we add the value 1 to this position, right? And we get that value and we return it to its calling parent. And then dpi. Okay, so I keep doing this mistake again and again. Now let's try to run this. Awesome. Now let's submit this one. Great. So we were able to solve it using DFS approach as well, and this is also of n squared time complexity, of m times and time complexity, and space complexity is also the same. Hope you liked my solution. Let me know in the comments down below. Thank you.